right, folks, we're back. We're going to work a couple of more titration problems for you today, just to sort of wrap that up and probably conclude our unit on acids and bases with this video. So let's just jump right into it by doing example 14 together. This time I want to know how many grams of solid calcium hydroxide would be needed to neutralize 72.6 milliliters of a 0.20 molar solution of hydrofluoric acid. Now, the first step, remember, is to write a balanced equation. So we have calcium hydroxide and hydrofluoric acid reacts to form. So calcium and fluorine will get together. Calcium, of course, is 2 positive. Fluorine is 1 negative, so we end up with CaF2. That's AQ. Will dissolve in water, and H and OH to get together. Notice there's an H here, but 2 OHs there, so we're going to end up making 2 waters, and for that we will need 2 HFs. So there's our balanced equation. Step 1 is done. Step 2, we want to get into moles, and so I have the volume and the molarity of my acid. So let's write this volume in liters. Wouldn't 72.6 milliliters be 0.0726 liters? So 0.0726 liters times the molarity of HF, 0.20 moles of HF per liter. So liters are gone, and I have moles of hydrofluoric acid. Step 3, let's go from moles of what I know to moles of what I'm after. So we're going to get into moles of CaOH2, and we'll use the coefficients from the balanced equation for that. It's like there's 2 moles of HF for every 1 calcium hydroxide, and that gets us out of moles of HF and into moles of calcium hydroxide. Now our desired unit this time is grams of calcium hydroxide. So we'll put moles of calcium hydroxide on the bottom, and we'll get into grams of calcium hydroxide. So let's go ahead and figure out the formula weight of calcium hydroxide. That shouldn't be too bad. Haven't done this in a little while. Let's go to our periodic table. We will find calcium, and there's 1 calcium. Looks like it is 40.08 plus, let's see what else we have here. We have 2 oxygens and 2 hydrogens as well. So oxygen, 16.00, and there are 2 of those. And hydrogen, 1.01, and there are 2 of those. So we get 74.1 for the formula weight of calcium hydroxide. All right, that gets us out of moles and into our desired unit, grams of calcium hydroxide. So let's do the math. We have 0.0726 times 0.2 divided by 2 times 74.1. So it looks like we would need 0.538 grams of calcium hydroxide to neutralize that acid. You feeling pretty good about this? That's our third neutralization reaction that we've done. We're going to do another one, but hopefully you're feeling pretty good about it right now. Alrighty, let's take a look at the next problem. Here, we're going to find the molecular weight of an acid by doing a titration. We're actually doing this lab in class soon, so you'll have this to look forward to. This will be a nice addition to your notes that'll help you with that lab. So what I want to do on example 15 is I want to find the molecular weight. Now, to find molecular weight, kiddos, we need to know 2 things. Molecular weight has the units grams per mole. Right? The molecular weight of a substance would be its weight in grams per mole. So I need to know 2 things, the number of grams and the number of moles. Then I'll divide grams by moles and I'll have my molecular weight. So in this problem, I have 0.500 grams of this unknown acid, and it's neutralized by 37 milliliters of 0.2 molar sodium hydroxide. So to find my molecular weight, it looks like I have the gram part there, 0.500 grams. So I just need to find out how many moles of acid I have. I can take grams divided by moles, and I will have the molecular weight of that unknown acid. Now, since I don't know the acid, I have to write a generic equation, so I'm just going to call it HX, and I'm reacting it with sodium hydroxide. Now, it's monoprotic, which means we only have one hydrogen. So that means I'll only need one sodium hydroxide. So this equation is balanced as it's written. It's a nice, pretty 1-to-1 mole ratio. So our equation's written, so let's move on to the second step, which is getting into moles. And I have the volume and molarity of my base. So let's write that volume in liters. Wouldn't that be 0.0370 liters times the molarity, 0.200 moles of NaOH per liter. So we want to now go from moles of NaOH to moles of what we're after, which of course is our unknown acid, HX. And that ratio is 1-to-1. So liters are gone, moles of sodium hydroxide are gone, and I have moles of my acid, which in this problem is what I need to finish the problem. So let's see what we have here. 0.0370 times 0.200 gives us 0.00740 moles of acid. So our molecular weight will be our 0.500 grams of acid, which was given in the problem, divided by 0.00740 moles of acid, and we will have grams per mole, our molecular weight. So let's see what that is. 0.5 divided by 0.00740 gives me a molecular weight of 67.6 grams per mole. Pretty easy, don't you think? Now, we're going to be doing this in the laboratory. We'll be doing a titration, just like in the last video that you saw. We'll be using some base, and we'll be titrating some solid acid. So we'll know the weight of our acid, and we'll know the molarity and volume of base, and we should be able to do that titration. It'll be a fun lab. I think you'll like it. All right, just a note about something called titration curves. In this first image here, we have a titration curve for a strong acid, HCl, with a strong base, sodium hydroxide. Now, when a strong acid and strong base react with each other, remember the net ionic equation is H plus and OH minus makes water. At the equivalence point, we have water and we have a neutral salt produced. In this case, it would be sodium chloride. So the pH at the equivalence point, now that would be the pH when I have equal moles of acid and base added to each other, would be 7. Okay, so bromothymol blue as an indicator, that will indicate a pH of 7. We can also use phenolphthalein. Phenolphthalein changes pH right around 8.5, and you can see that would still work. It's still this vertical portion of my titration curve here. At any rate, when you titrate a strong acid with a strong base, the pH at the equivalence point will be 7. And you can see on this titration curve, we have pH on the y-axis versus volume of base that we add. So initially, my pH is quite low because I have a strong acid in there, don't I? And then as I begin to add base, the pH rises. And at the equivalence point, you get a sharp increase in pH. And so this sharp increase section, when you go halfway up there, that represents the equivalence point. And once again, the pH is 7, we titrate a strong acid with a strong base. But we don't always titrate a strong acid with a strong base. Take a look at this second image. Here we have formic acid and sodium hydroxide. So the equation for this would be HCOOH, that's our formic acid, and I leave that together as a molecule. Remember, weak acids stick together. And I have Na plus and OH minus. That's a strong base, so they dissociate in water. And we end up with sodium formate, which is Na plus, all sodium compounds are soluble, and COOH negatives. And of course we end up with water being formed. Now the spectator would be sodium here. So you can see in this net ionic equation, on this example, when I have equal moles of acid and base, I do make water, but I also make this negative ion. And negative ions, if you recall from our hydrolysis discussion, will react with water and they will tear it apart. They will actually attract, this is negative, it'll attract the positive part of water and form HCOOH, and you're left with hydroxides. So it ends up that the pH at the equivalence point, when you titrate a weak acid with a strong base, will be basic because you have this basic salt that's produced. So you can see in this pH curve, my pH starts quite a bit higher because it's a weak acid. And as I add base, the pH slowly rises, and we get this sharp increase at the equivalence point. Half this distance here gives me a pH of about 8.5 or 9 at the equivalence point, which is basic. So I'm just showing you this just to let you know that just because you have equal amounts of acid added to base does not mean the pH will be 7. Sometimes it ends up being higher than 7, sometimes lower than 7. Okay, so I just make that statement down here. You might think that all titrations have an equivalence point of 7 because that's the point which concentrations of hydrogen and hydroxide ions are equal. However, that's not the case. Some titrations have an equivalence points at pH values less than 7. Some could be greater than 7. These differences occur because we have a reaction between the newly formed salt and water, and we call that hydrolysis. Okay? All right, folks, that'll wrap up our acid and base chapter. We'll start a new chapter soon. Talk to you later. Bye-bye.